Okay, so in this lecture, we are gonna discuss the concept of volume, and this notion will be essentially required when we'll be studying Minkowski's theorem in the next lecture. So, um, like we know that how volume works in case of a three-dimensional geometrical figure, a three-dimensional Euclidean geometrical figure, and we also have some sort of a notion about the two-dimensional and the one-dimensional analogues of volume. So let me just be a bit brief about what typically volume is. For example, suppose we are in one-dimensional plane. Suppose we are in a one-dimensional surface, and suppose this is the line we are considering, and so simply we can consider this to be just r, and the elementary Euclidean figure we might be considering on a one dimensional surface is just a line segment, a segment of this line. So let this be a, let this be b, and in this case quite obviously the volume analog, the thing which which resembles the concept of a volume which we have studied in case of the three dimensional Euclidean elementary figures, is just the length, of the segment, and in this case it will be just b minus a. Important thing to observe is that this b minus a can also be interpreted as the integration over this line. So suppose I write this line as L, so over this line L of just dx, right? If you know very elementary integration, this is quite observable. Clear? I could have also written this simply as the usual notation we would follow in this case, which is the integration over a to b dx, but I want to specify that we are integrating over this straight line which joins a and b. So this is quite easy to observe. Now let us move on to the two dimensional plane. So suppose I talk about the two dimensional surface. Whenever we study the concepts of any sort of an area, so let me just just give it for the, in this case the volume analog, which is quite intuitive as well, is just the area enclosed. Okay. Now the thing to follow, if you have studied Riemann integration, or if you have studied your school level areas, concepts of area, you will see that the notion of area primarily depends on the area of a rectangle. Okay. Because whenever you try to find out the area of any object, you always try to find it using rectangles or using grids. For example, you will recall that I guess in class 10 or something, you used to have a project where you were given a leaf which you used to call lamina, and you were asked to find the volume of it, and the procedure you would primarily follow is that you used to draw this lamina on the grid paper of your project sheets you had, right? If I'm not wrong, on the grid side, only on the green grids drawn on your project sheets. So basically what you used to do is that you used to just just break it down into rectangles, and that's exactly the thing you would do. I should draw it in some other way. So let me just write this in a bit far. So this was what you called a lamina. You can think of it just as a simple sheet, and what you used to do is that you used to break it down into simple rectangles. So let me be fast a bit. So this is what you guys used to do. Okay, and then used to verify how many of these grids are completely inside this lamina. So you will find this one, then you will find this one, you will find this one, this one, this one, this one, then you will find this one, you will find this one. I guess this is also completely inside, and the ones which are not completely inside, you can just approximate them to be half rectangles of some sort, and in this way you can approximate the area of this lamina. Now this lamina was a very irregular figure, and you tried to regularize it using forming rectangles on that. Okay. So the elementary notion of area of any arbitrary two-dimensional figure primarily lies on the notion of area of a rectangle. And how can we typically find the area of a rectangle if I essentially speak? So suppose I have this R2. Suppose this is your usual R2, and I try to draw an arbitrary rectangle here. Now a rectangle is primarily the cross product or the Cartesian product. I should rather use the term the Cartesian product of two intervals. Okay. So suppose I choose an interval of this sort. Suppose I choose an interval, say A1 and say B1, and let me draw a line like this. Okay, this would do, and I choose two other intervals on the other real axis. I have two real axes to form the real plane. So suppose I have here, let's say let's say B2, and if I continue this line out, yeah, this would do, and I have another line segment, I say to be A2, and you will see that you have an intersection which is exactly, this intersection is exactly a rectangle, where you have its length to be B1 minus A1 and its breadth to be B2 minus A2, and you know that the by your elementary formulas of area, the area of, say, this is A, B, C and D, the area of A, B, C and D is nothing but B1 minus A1 times B2 minus A2, length into breadth, it will do. But as I know that I want to generalize this to an n dimensional surface, so I need some sort of a formula which is which avoids these very specific points to find out the area. And for that you can easily observe that I know I can integrate to find lengths. So I can find B1 minus A1 by just integrating over this line, over the first real axis, to get so let this line be L1, let's say. So I can integrate it over L1 over, say, dx1, where the coordinates of the horizontal real axis are given by dx1, and I can further integrate by L2, integrate over L2, where I can just take this line to be L2, and I integrate over dx2, where x2 represents the coordinates over the other real axis. Okay. In short, I can typically do it in a way that I can typically do it as integration. So L1 and L2, if I cross L1 and L2, so I'll typically get this region, right? So I can just write this as, let's say, x is, or let this be R. Typically let this be R. So I get the region R. I integrate over this region over the of the coordinates dx1 and dx2. I hope you are getting the point. Clear? So this will give me the volume of R. This will give me the volume of R, and we just tend to generalize this out. So to generalize this, we get the following definition. So let's choose a region from Rn. The volume Vx is defined as the value integration over x dx1 dx2 till dxn, where, so as I see that each of these xi's are just coordinates, where this x1 x2 till xn are coordinates. Okay, and I hope you have you can already visualize how this volume exactly works. So it's a simple generalization of our elementary figures. Clear? Okay. So typically now we are intended to see that how area works in case of the torus, because torus is not immediately an Euclidean space, it is some sort of a topological space constructed from the Euclidean space, and so there is some topological connection between them. In fact, we have seen that it is bijective, to the fundamental domain, and we further know that the fundamental domain, when scaled by the points of the lattice, I will get the whole Euclidean space. So keeping that in mind, I can define, or I can try to define, the volume over over any region over the torus. Okay, so we started like this. So suppose L is a n dimensional lattice, is a n dimensional lattice. Okay, then we know, so this is just a recall of what we did in the previous lecture, that so we know that Rn quotiented with L as a quotient group is isomorphic to Tn, where Tn represents direct product of n copies of S. S represents the unit circle, which we call the n dimensional torus. Okay. Further, we are also seen that further, if T is the fundamental domain, so if T is the fundamental domain of L, then we know that there is a bijection phi from T to Tn, okay, is a bijection. And the function, how it works, we have seen this in the previous lecture. So if you quickly recall what we specifically used to how we elementary mapped this bijection was that I chose a certain generator of L, which would also come out to be the basis of Rn, and then choosing any linear combination, I would just map it to component wise, I will just map it to the unit circle. Okay. So when I restrict that to T, I will get an injective map, because in that case the kernel will become 0. Clear? So this leads us to the following definition. For all x in Tn, whenever I choose a subset of Tn, or rather you can think of it as a region from Tn, we define the volume of Vx, sorry, I should use the volume Vx, it's grammatically incorrect. So the volume Vx by, now what is your what should be the standard procedure to define such a volume? See, let me just give a so suppose this is your fundamental domain. Suppose this is your fundamental domain. Okay, this is your fundamental domain you have, and I know that it's surjective to the n dimensional torus. Okay, so assume it like this. Now what I try to do is that I choose a region, I choose some sort of a region, say here, but I know nothing about how to define a volume in this case. I don't know how to integrate over this torus, but I know the concepts of integration over the Euclidean space, and the fundamental domain, it primarily lies inside the Euclidean space. So what I try to do is that I just map it back to the fundamental domain to get some sort of a region, in this case let's say some sort of a region like this, and since this region lies primarily inside the Euclidean space, I can talk about the volume of this inverse mapping of x. Okay, this has a well defined volume, this might have a well defined volume, every elementary figure might not have a well defined volume, this might have a well defined volume, and I can define this in this way. So the volume Vx, we define the volume Vx by, so Vx is defined as the volume of the inverse image of x inside the fundamental domain, further which exists, and it will exist if and only if the volume of this inverse map exists, inverse image exists, so which exists if and only if this region phi inverse x has a volume, and it must have a volume in Rn, and the volume of this primarily obeys the definition of volume, which is the multiple integration over each of these coordinates over the region we are required to find the volume. Is this part clear? Okay. Now let's move on to the next immediate observation. Let gamma be the natural quotient map from Rn to Tn, because Tn can be identified as the quotient group Rn mod L. Okay, so this is the natural map. Then observe that whenever I choose any element out from Rn, I can consider a ball of radius epsilon centered about x, such that for all x which is inside this closed ball of radius epsilon and centered about x, for which volume exists, we have the volume of x to be the volume of gamma of x. Okay. So gamma just maps the regions from the regions in the Euclidean space to the region in the torus, right? So in this case we can also observe this out. So gamma just maps Rn to Tn with the kernel L, where all the lattice points are identified together. So if I choose a region, a bounded region, a bounded subset of Rn, then I can just map the bounded subset of Rn using the natural map to the torus, to the n dimensional torus, and I can talk about the volume in that case, because the volume of x exists in Rn. Is this part clear? Okay. Now this is a very important observation, that if an injective map is, so this is an important term, is locally volume preserving, then it is volume preserving. Okay. And in the next, volume preserving, I typically means globally volume preserving. So what I typically mean, let's discuss a bit here. So what do we mean by locally volume preserving? See, suppose this is your Rn. Okay, this is your Rn, or let me not be talking about Rn as well. Suppose I take your torus. Suppose this is a two-dimensional torus, for example. Now I know that this comes out to be a map from Rn with kernel as the points of the lattice. If I choose a small region over this torus, an extremely small region over this torus, you will see that this torus is just a flat portion. It is just a flat portion. Okay. You can imagine this to be any small surface over any small region over the surface of a donut. Okay. So this is a very flat portion, and if it is a flat portion, so it topologically, or you can also think it to be just visually, resembles an equivalent small region, in Rn. Clear? Because we know that Rn is flat, right? Any Euclidean space is flat. You can talk about R2 in this case, just R2. If I choose any small portion of the surface of a donut, then that is primarily flat, right? It seems to be a set coming from the standard Euclidean plane R2, right? So therefore, if I choose any small surface from R2, which is obviously flat, and I see the image it carries over to the torus, then it will still be a small portion, a small region over the torus, which is still flat. Therefore, the volumes will be same, right? The volumes will be same. But if I choose a large region over R2, if I choose a large region, so suppose this is your R2, and if I choose a large region over R2, okay, if I choose a large region over R2, okay, then this region will not remain flat in the torus, but instead it will get, some sort of curved it will get. So it will get some sort of like this, for example. It will get some sort of curved, and in this case it won't preserve the volume it would be having inside R2, right? So in other words, the n dimensional torus is locally flat, okay, and that's why we say that it's locally volume preserving. Okay, if you have studied differential topology, you will see that this torus, they easily form a manifold, because locally they are homeomorphic to An n-dimensional torus is locally homeomorphic to n-dimensional Euclidean space, you will see. Okay. The thing to observe here is that whenever I take a very small region from whenever I take a very small region from the torus, it will a small open set. If I think of it as a small open set from the torus, it will map homeomorphically or topologically equivalently to an open set in the whatever dimension of Euclidean space you will eventually get. So the thing is that locally the torus resembles the standard Euclidean space, but globally it's curved. So in language I can say this to be that Tn is locally flat but globally curved, which is exactly what I wanted to be. Okay. Therefore, if so, this is the goal which I wanted to express. So if I map a small portion of Rn to Tn, the image won't get distorted. The image won't get distorted, and that's why I can talk about the fact that it's volume preserving. I hope you get the point. Okay. And if I talk about injective maps, now carefully observe this. So let me just take the examples of a torus as well and an arbitrary region. Suppose this is an arbitrary region, let's say X, and say this is your torus. Okay, this is your torus, and suppose I have an arbitrary map from Rn to Tn. I restrict that map to X and I see that this map is injective. That's what I wanted to mean. I see that this map is injective. Okay. Then I'll see that the images are still the same. Okay. The volume of X will be exactly the volume of it when it is mapped to the torus. In other words, the second statement which I had, that if an injective map is locally volume preserving, then it is volume preserving. So suppose I choose R2, simply let me mean what I said, and suppose I choose multiple regions over here. I choose multiple regions. All of these regions are bounded inside some ball. So all of these regions are bounded inside some balls. Okay. And I have that a map from Rn to Tn is injective. So if I map this, it will map to some sort of, say, this area. If I map this, it will get mapped to some sort of this area. If I map this, I'll get to some sort of this area. But if I continue tracing these areas in the R2 plane, I will eventually cover the whole R2 plane, and the areas of these small sections which we have chosen, their volumes are preserved when I have mapped them to the torus. In other words, these small sections will cover the whole of the torus as well, and any arbitrary region you now talk about, it will the volume will still be preserved, because I can just think of them as as the union of these small sections whose volumes are being preserved, because it is locally volume preserving. That is the reason why whenever you have an injective map which is locally volume preserving, then it is volume preserving. I hope you get this point, because I will get distinct map, right? Because if I have an injective map, I will get distinct map. So since I am getting distinct maps, they need to be volume preserving, because they are just pieces of the same volume which I have just taken from R2 and placed inside the torus. So the R2 gradually vanishes as I brings out the puzzle pieces, and the torus is constructed completely as I put these puzzle pieces back. Okay. I guess this clarifies what I wanted to say. Okay. But is the what can I say, what can I clarify more about this theorem? That is, if an injective map is locally volume preserving, then it is volume preserving. Suppose I have a map which is not volume preserving. What can I say at that point? Which leads us to the theorem, which is the final discussion of this lecture. And with this theorem we will end the part of the quotient torus, and we will from the next lecture we will move on to the concepts of the Minkowski's theorem. So the theorem is as follows. If wait a minute. So if X is a bounded set, is a bounded subset of Rn, and the volume of X exists, and if the volume of the image of X inside the torus coming from Rn is not equal to the volume of X, that is we cannot, the volume is not preserved, then the map gamma when restricted to X, it cannot be injected. It cannot be injected. And we will immediately see the proof of it. Okay. So let's see the proof of this. So what I'm trying to do is that I am taking, so first thing first, I know that, so these things are to be kept in mind, that T plus L, these cover Rn, and each of these T plus L's, they are basically, they resemble grids, right? So what we are typically doing is that we are gridding out Rn, and then we are doing our job. Okay, 1 second. Yeah. Okay, let's start with this. Okay, so let's start with the proof. So our usual procedure will be to follow from contradiction. So suppose gamma X is injective. Okay. Now X being bounded, not X1, X being bounded, intersects only a finite number of these TLs, only a finite number of sets T plus Ls. Okay. Yeah. And the reason is that just T is just a fundamental domain and L are just points of the lattice. So I'll get, you know, distinct grids. Let me just clarify this diagrammatically. I'll try to express this as much as I can diagrammatically. It's a bit complicated to talk about, whatever. So okay, rather not do it like this, rather let me form a grid to be precise. So yeah, so I have the sets T plus L of this form. Okay, so I am just gridding out this portion. I'm sorry if I am just taking a bit time to form these grids, but it's for your benefit, mine as well. Okay, yeah. So I'm choosing X to be inside some bounded set. So X, how can X typically look like? So X might typically look like this, say like this. Okay, so I just consider this like this. Okay, so this is how X typically looks like. Okay, and then what I do is that, yeah, so it intersects only a finite number of these T plus L's. So I'll choose these each individual intersection to be XL. So let XL to be the intersections, let's say X intersection T plus L. Okay, so suppose this is your okay, and then let me just clarify this. So I'll get only finitely many such L's, right, where this intersection takes place. So I can write X to be the union of these XLI's, and there I'll get only finitely many such i's. So I can write it as I is equals to 1 to n. Okay, so in this case I have 4 of these intersections, if you carefully notice. So I can just take this to be, say, XL1, this to be XL2, then this to be XL3, and this then this to be XL4. Okay, these are the intersections I have. Clear? So these are the intersections primarily. So this is one intersection and other intersections follow. I guess now this part is quite observable. Now what I do is that I bring out each of these intersections to T. Okay, suppose this is just T. this is just your T, and to bring all these intersections to T, I just need to cancel out the lattice points the fundamental domain has been scaled with, right. So for each Li, define YLI. So what I am trying to do is that I am taking just each of these XLIs and I am just bringing them down to the fundamental domain by cancelling out the scaling factor, the lattice point Li. Okay. So if I do that, I will bring all of them down to these this T. The thing to keep in mind is that the map gamma is injective. If you recall, the map gamma is injective. So if gamma is injective, that typically follows. Okay, first let me clarify this part. So such that each of these YLIs, they fall inside the fundamental domain. Okay. Now since gamma of x minus Li must be exactly equal to gamma of x, which quite follows immediately because of the because gamma is just the natural map from Rn to Tn with kernel L. This happens for all x in Rn. These YLIs are disjoint by the injectivity of gamma, right. So therefore I'll get YLIs to be say sort of like this region I have, then I'll have some sort of a region like, let's say this, I'll have some sort of a region like say this, and I'll have some sort of a region like say this. Okay. Suppose this is my YL1, this region is my YL2, this region is my YL3, and this region is my YL4. Clear? Okay. Okay. Now what more we can do from this? Okay. Now observe that now the volume of each of these XLIs, is exactly same to the volume of each of these YLIs, right. You can easily follow it from this diagram. So the volume of each of these XLIs exactly equals the volume of each of these YLIs. Okay, and this happens for all I. In fact, also if you observe that if I map each of these XLIs to the torus, it eventually maps to the image of YLIs under the mapping, under this bijective mapping of the fundamental domain. So eventually what I get is that all of these XLIs, when collectively mapped to the torus, and all of these YLIs are collectively mapped to the torus, they will form the same image. They will form the same image. That's the exactly thing to observe. So where this phi is the bijection T to Tn. But now observe, but then when I check the volume of the image of X as a whole under gamma, it is just the volume of the union of these XLIs under gamma, but then gamma of the union of these XLIs is just the union of these YLIs. But we know that these YLIs are disjoint, so this is just the summation of the volume of these YLIs. This follows from disjointness. By disjointness, but then this will say that so the volume of these YLIs will equal the volume of these XLIs. This is also we have immediately observed. I should have written LIs in the subscript, it seems not good. YLIs, yeah. So YLIs, and then this should equal the volume of X, which is a contradiction. Because we have assumed that the volume is not preserved, right. This is given in theorem itself. Okay. Therefore this map gamma, this cannot be injective. Gamma when restricted to X, this cannot be injective. What typically happens is that this figure, so let me just apply a star here. wait a minute, so I apply a star here, then both of these under the respective maps will eventually get mapped to, so I have these two of the circles, right, if you recall. So this is one of the circles I had in constructing the torus, and this was another circle I had when I constructed torus. So these will eventually get mapped to the same figure. Okay. So the case which physically follows is that if a locally volume preserving map does not preserve volume globally, so this is our final conclusion, that if a locally volume preserving map does not preserve volume globally, then it cannot be injective. Clear? Okay. So I hope this explanation was was highly clarified. In the next lecture, we will start with the primary goal of this series, the Minkowski's theorem. After having studied the Minkowski's theorem, and using the Minkowski's theorem we will study the 2 squared theorem and the 4 squared theorem, then we will be trying to moving on to the concepts of the geometrical representation of algebraic numbers, which is not that difficult to talk about. Okay. And after that, if I get time, I'll also talk about the class groups and class numbers. Okay. So meet you guys in the next lecture.